In the Restless Earth Part 1, we get some answers to big questions about our planet. We find out how did our planet form, how heat is generated on the planet, how the layers of the planet formed, where did all that water come from, and then we find out a little bit more about the layers and how do we know all this stuff, which I'm hoping that that's a question you asked yourself as you were reading. So let's dive into each of those questions separately. I guess the shortest answer to how did Earth form would be through a solar nebula and gravity. With the cloud of gas and dust pulling together, the solar nebula tended to collapse and turn into a disk of rotating materials. The most dense materials moved to the center of the solar system, and that would be the star of our solar system, the sun. The less dense materials moved to the outside of the solar system, and those would be the gas giants. But along with Earth, the inner planets created these rocky planets that were composed of rock and metals. So while our solar system was forming billions of years ago, so was Earth, all through a process of differentiation and gravitational pull, bringing materials together. As you can imagine, this whole process of gravity pulling materials together, it definitely heated up the objects. So our planet is hot at its core, but at one time it was hot all over. And the reason it has this heat is for three big parts. One big reason our planet and the sun and the rest of the objects in the solar system were hot was due to the collision of materials. Whenever you have kinetic energy or the energy of motion and objects hitting each other, that energy transfers into some thermal energy as well. Along with the thermal energy created with the collisions, thermal energy was transferred just due to the gravitational potential energy. Those objects on the outside of the planet and around it, as they move to the center or to the core, there's this transfer of the potential energy into thermal energy there. And lastly, you may remember back talking about radioactive decay. And there are certain elements that as they decay, they transfer energy over into thermal energy as well. So uranium, thorium, potassium, those are the elements that as they decay on the planet, it generates this thermal energy that keeps our planet nice and toasty. Now, our planet started out as being pretty uniform with a mix of rock and materials, and because it was partially melted, the objects could kind of flow and move around the Earth. But as the Earth cooled and as gravity pulled the more dense objects to the middle and the less dense objects stayed towards the outside, we had a process called planetary differentiation take place. Through the process of planetary differentiation, we developed into the planet that we have today, where the most dense materials form our core, and it gets less dense as you move outward from there. So I'm hoping that one of your next questions is, where did all the water on planet Earth come from? Because we can see different planets around our solar system, and they don't have water. So where did it come from? Well, one major way is through the volcanoes. There were gases that were trapped in the interior of the Earth as it was forming. And so as the materials move around and the gases get released, they get spewed up into the atmosphere, and you have everything from hydrogen and nitrogen to carbon dioxide, and that's how part of our atmosphere developed. Scientists also believe that some of the gases brought to our planet came from objects from space. So as they made impact onto our planet, they transferred some of their material. In any case, this water is what helps sustain the diversity of life on our planet, among other things. Now, I know it seems like over and over and over again we talk to you about how the Earth has layers, and you've seen diagram after diagram. One thing to think about is our planet's actually kind of like a hard-boiled egg. You have the different composition at different parts of the planet, and that chemical makeup makes these distinct layers. But while the layers are distinct, many times we think that they're exactly perfectly round and spherical and everything, but that's not exactly true. our layers on the planet are not uniform. So they can have areas where they kind of look a little mixed up, and they are. The crust of the planet is made up of different materials, and silicates are one of them. We have thin, dense oceanic crust, and we have thicker, less dense continental crust. You can see in the picture the oceanic crust subducting or moving underneath the continental crust, because as they converge or move together, the thinner, more dense oceanic crust will slide underneath the continental crust. And here's something to think about. The thickest part of our planet's crust is the Himalayan mountain range. If you think about it, that crust is from the very top peak of the mountains all the way down through. It's not just what we can see, it's even below that. Now the mantle is a little more dense. It has silicates, but it also has elements like magnesium and iron. And the composition of the core is the most dense, made up of iron and nickel. Something else that I hope you remember reading is that as you travel down into the interior of the crust, the temperature also goes up. There's more dense packed materials, and there's more radioactive decay happening, and it's just heated up as you go down into the core. Now, one final thing about layers. Do you have to memorize all 5 of the layers? Well, you could if you want to remember LAMOCIC. That's how I remember the lithosphere, asthenosphere, mesosphere, the outer core, and the inner core. But let's be honest, you could probably Google that. I am more concerned about whether you know the answer to this question, and that is, how do we know all this stuff? Because we can't drill to the core of the planet, so how do we know what it's like? One of the best indicators of what the planet is like is the evidence and the data that we get from earthquakes. When the planet moves, energy is transferred, and those seismic waves travel. Now, when earthquakes happen, they actually happen in stages. You first get a primary wave, what people call a P wave, to move from the focus or the start of the earthquake out to the surrounding materials. Now, primary waves travel through all kinds of materials. So the different layers of the planets, they might speed up or slow down the primary waves, but the rock that gets compressed and the liquid that gets compressed, it's going through all parts of the planet. So you can feel a primary wave from an earthquake on the other side of the planet. Secondary waves, also called S waves, are a little bit different. They only travel through solid materials. So when these seismic waves come into play with the outer core, which is liquid, they actually get blocked. So you won't see secondary waves all the way on the other side of the planet. And secondary waves move the rock, instead of like squeezing it and compressing it, these move rocks from side to side. So P waves and S waves, while they are both created by earthquakes and they both start out from the focus and travel through solid materials, only primary waves can be found all around the planet from the focus because they travel through all the different materials. Because of that, the seismic sensors like seismographs and all the different machinery that we have set up around the planet, they will have these gaps of seismic waves. You'll have what are called shadow zones. Because S waves don't travel through the core, there's a large S wave shadow zone on the opposite side of the planet from where the earthquake occurred. And because P waves kind of get bent, they slow down through some of the material, there'll be P wave shadow zones in spots. So while seismic waves are a great way to know what's inside the planet, it's not the only way we know what's inside the planet. We also use evidence from volcanic eruptions. When some volcanoes erupt, they blow out rocks from with the magma and the hot gases and everything. And so we investigate those rocks and see what they're made of. And scientists are always excited to have meteorites come through our planet, as long as they don't do too much damage, because they tell us what the composition of other objects in our solar system are made of, and that gives us an indication of what our planet is made of. Another great piece of evidence as to what the planet is made of is through our density. The rocks at the crust are about 2.8 grams per centimeters cubed. But by looking at Earth's gravitational pull on other objects, the average density for the planet is 5.5 grams per cubic centimeters. So we know that there is more dense material at the middle to get this average density. Finally, I know that you have heard about our planet having a magnetic field. Well, that magnetic field is protecting us, and it's super important. It is created by that inner and outer core and the rotation between them. So because we have that sort of moving core, we have a magnetic field around the planet. Now, that was just a quick overview of some of the big ideas in the first section, but I know you had probably even more information that you had in your mind, and that's good. So in the first part of the Restless Earth section, it's all about evidence. How do we know what we know about our planet? Through direct and indirect evidence.